It's my pleasure to welcome you to the Program Logics and Memory Models session this morning. The first talk is going to be on compound memory models, and it's going to be given by Andrés Hoens. He's at the University of Edinburgh, but will be soon moving to Amsterdam. Cool. Take it away.
Okay, thanks for the introduction. Hi, everyone. It's nice to be here. Today I'm going to talk about compound memory models. And before I tell you what the compound part means, let's just briefly go over what I mean by memory models, or what are memory models. So we've all seen these interleaving semantics. When we try to reason about concurrent programs, we think of sequential programs that execute on their own, and then the execution of the entire system is usually thought of as the interleaving of the sequential programs, right? And an important component of this model is that we cannot reorder things. Things happen just like they happen in the sequential program, they happen in the interleaved semantics. So this is a memory model. This is called sequential consistency. And while it's a very important, interesting model, it's also not what hardware does at all. So all hardware, basically all major architectures have more relaxed memory models than this. So for example, an x86 processor might allow some reorderings for performance, whereas a different architecture, whereas it would disallow others, and a different architecture, maybe ARM, might allow more of those behaviors. So a memory model is just the rules that tell us what behaviors are allowed to be visible in our cores and which ones are disallowed. So there's, as I was alluding to before, there's different architectures, and all of them have different memory models. And we, as a research community, many people in this room have also spent decades studying and understanding these memory models for different architectures. And we have a clear understanding of the individual ones for some of them. But what's happening now is that people are starting to combine these models. So if you look at the new announcement from NVIDIA, the Grace Hopper architecture, that's not a GPU. It's actually a system that has a GPU, but also a CPU integrated with them. So it's got a CPU, a GPU, and these two have individually different memory models. But interestingly, they are also having to start sharing models. So they have a current interconnect between them. So that brings us to the problem, I guess, first of what compound memory models should be. If we take this picture the diagram that I'm showing you, and we try to abstract it away a little bit, instead of the ARM CPU, the NVIDIA GPU, we have two architectures. Let's call them the blue and the orange one, and they have an interconnect that makes them share memory between them, and that tells us what's the that gives us the question: what is the shared memory model of the two? What's the compound model of these two? So what should the specification be? Even if we know the individual memory models, it doesn't mean that that we know what the compound one will be. Okay, so why should we care about this? Even if we think of this compound memory models, so even if we have when we build an architecture like this, we will want to program this, of course. And so if you think of programming this, we will want to do it not in assembly directly, but we'll have a higher level language, or C or a higher level language, to program that. And we will have to compile down that to the architecture. So we want to know that what we're doing is correct, this compilation is correct, and we need a specification for the architecture to be sure that what we're compiling is correct. And these specifications, as I was alluding to, they give us a larger design space of possible ways that we can combine the memory models. And we think when we have a large design space like this, we want to think carefully about what exactly we want as a specification. And once we've decided what the specification is, we also need that to validate our hardware designs, for example, to make sure that they adhere to this compound memory model. So why is it difficult to come up with the right abstraction? What are the challenges that we have that? Well, we can think of the simple options that you might think of the compound memory model and see why they might not be ideal. So one of the simplest one is we already have 2 memory models there. Why don't we take one of them and just use that? So if we take the blue one, and let's say that's the CPU, that's the stronger of the model, so that stronger means it allows less behaviors, and note that they might be incomparable, but let's ignore that for now. If the model is too strong, if you take the stronger of the 2 models, then what happens to the other architecture, the orange one, the GPU, for example, then we might have to modify that, because it now has to adhere to a stronger memory model. We have to understand what's happening there. And that's going to give us worse performance, and the hardware vendors don't want to modify their designs just to join them together. So that's probably not a good idea. But on the other hand, if the model is too weak, if we say, okay, we had 2 models, we don't want to take the stronger one, let's just take the weaker of the 2 models as the specification. Well, now if we have a weaker memory model, then we might have a program that we originally designed just for the CPU, for the blue architecture, and now it suddenly stops working just because we're working on a compound system, just because we put it together with something else. The specification is weaker, and suddenly our program stops working. So more generally, the compiler mapping is going to be wrong once we do that. So we cannot just take the compilers as they are, compiled to the 2 individual architectures, and run things in the compound machine if we take a too weak model. And particularly difficult of this is the synchronization between the 2. So this sounds fairly abstract at this level, but I hope that I've conveyed that it's complicated to get these things right. I think the easiest way to understand the problems here is to look at an example. So we can think of an example of this is a famous litmus test, or a common one that's called message passing, where we have 2 variables, x and y, and they write, they've been written to on the CPU side, on the GPU side, for example. Let's say the GPU is running on a PTX memory model, which is the NVIDIA one. And then on the other side, the 2 variables are read, but in the opposite order. So they synchronize using the variable y, and once we've read 1 on the variable y, we want to understand, could we still read the uninitialized value of 0 on the variable x on the CPU side? We would hope this will not be the case in this case. We might have so we have a fence here on the CPU, on the GPU side, but we don't have a memory fence on the CPU side. And if you think about this is what you'd get if you compile a release acquire program in say language level semantics like C11. Because while on the GPU side, the PTX has a release consistency-like model, so you have a release fence there. So that part's clear, but on the x86 side, you would not get a memory fence because TSO already preserves this read-to-read ordering from the preserved program ordering of TSO. So compiling that normally wouldn't give you a fence here. So we want to be able to disallow this behavior without adding a fence on the x86 side. And that's not obvious. If we just took the weaker memory model, for example, that wouldn't work. So the more general problem that we have here is compositionality, the problem of compositionality. So we have existing memory models that we have already are not modular. So they're not modular in the architecture, in the structured set architecture. So there's no obvious way to compose the existing memory models that we have, because or one reason we think of this is because they have a global view of the entire execution of your program, and so the rules apply to the entire execution. So what our approach is that we think of, try to achieve this compositionality by thinking of thread local semantics for the individual architectures. And that gives us a way to create a compound system by having the semantics of each individual thread defined, and then the system just has threads of different types. So how do we achieve this? We have an operational model that enables this principle. So operational, as in operational semantics. We have an operational model that gives us this principle, using this principle that we called local ordering by stalling on threads. And the key idea is, so as an operational model, we have these writes and reads. So this is, again, an abstraction of the litmus test we had before. And if we don't have a fence, the way the model works is that these writes can propagate to a different thread and give, so the write of y can be observed before the write of x here, because the write can propagate freely. But if we have a fence between them, then the fence is going to block this it's going to stall this write from propagating until the write of X has propagated, and that allows us to model behaviors, to model these kind of behaviors on a thread local fashion. Why thread local? Because the semantics of the fences are all specified just for that thread, and it doesn't care about what the other threads are, what kind of architecture they are. So modeling this at this level sounds simple, but there's a lot of other challenges that you have to acknowledge. Like fences, like we've seen before in different memory orderings, have other more complicated behaviors like cumulativity, A and B cumulativity. But there's also non-multi-copy atomicity and scoped accesses, which are important for GPU models. But we can all model all of these with carefully thought of operational model that's modular on the architecture and has these thread local operations. So what do we get from this? Well, what are the results of this work and what we've been thinking about here? Well, I think one of the main results is the question itself. What should the memory model of these compound systems be? What should compound memory models be? And I hope I've convinced you that the answer is not trivial. We have to think about it hard and make sure that we build what we want and don't end up with a sea of different memory models for different combinations. So our answer is this lost POP operational model, which is based on the previous POP model for ARM from a different group. And using this concrete combination of PTX and x86, we've also proven that the mappings are correct to these compound memory models by defining an axiomatic version of this model. So we've proven that a given set of mappings is correct for this given combination. We've also made sure that what we have is actually modeling faithfully. So we tested the individual components of these compound systems on x86 and PTX with the existing models for the individual architectures and made sure that they matched, and also for the combination to make sure that the compositionality property and the compiler mappings hold. But all of this is just mathematical models. What about actual hardware? The problem is that this hardware doesn't exist yet. So we cannot test it on hardware. What we could do is test it on a simulator, which is the next best thing that we have available. We tested it on a simulator provided by AMD based on Gen 5, and basically all the results on a different set of litmus tests agree with what our models say. Because we're on a simulator, we can also relax some invariants, like the single write to multiple reader invariant in the cache coherence protocol. And that actually breaks this message passing litmus test that we were talking about before. So while it's unclear exactly how that invariant plays, it goes into play here, it definitely doesn't give us the memory model that we want. So it's not clear that we won't automatically get the right thing if we just do it. So we have to think about this. So in conclusion, if we have heterogeneous systems, we want to build heterogeneous systems and make them share memory, we have to think about these compound memory models. And compositionality, as I hope I've convinced you, is an important property that we want to have in these. In order to have compiler mappings that work, in order to have unmodified hardware. And we do this with this loss principle, which is compositionality through this thread locality. So that's the end of my talk. Thank you. And I can take questions now.
Okay, so if you go up to the microphone and introduce yourself for questions, please.
Jean Pichon, Aarhus Universiteit. So you chose to write an operational model. And I was wondering whether you thought about writing an axiomatic model instead, because it seems to me kind of pretty clear how you would do that. You would take sort of preserved program order, PPO, or LOB, however you want to call it. Yeah. For each memory model, for each thread, you would have its memory model that dictates what LOB is, and then you just need to have to think about this sort of propagation effects, and this is where you need to think, but then you sort of get the local ordering for free. Have you thought at all in that direction?
Yeah, we've thought quite a bit. We wanted to make it work axiomatically because it's also easier to check and used by a lot of people. But the problem with the approach you're outlining is that it will work for models that are non-multi-copy, that are multi-copy atomic. But if you have non-multi-copy atomic behaviors, at least it's not clear to us how you would make it work with just joining the preserved program orders. We can talk about it more offline. We'd be very interested in making this work axiomatically, but
Okay,
Didn't know
thank
how
you
to
very much.
work. We tried.
Talk offline.
Okay, so I have one question. So when you kind of put these two models together and you've got your compound model, you've done a C++ mapping to this, but is there a sort of C++ feature you might want to add to try and help with like the fences or something? Is there something extra you might want to represent what you're doing?
I mean, I cannot think of one out of the top of my head. I would actually think you would not want to add anything. So ideally for the programmer, this should be completely transparent. You shouldn't think of that you're having a cache coherent system. So it should just work. So you write your C11 programs and the compiler makes everything work. And you don't have to have an additional layer of indirection or of abstraction that you have to think about that you're compounding systems. That's what I would think about out of the top of my head. But if you have anything concrete, that'd be interesting to think about too.
Cool.
Thanks.
Thanks. Okay, let's thank the featured speaker.